Hello, everybody. Thanks for the nice presentation. I am Manuela Chessa. I'm from University of Genova. I will start with a very brief background. I come from Genova. Genova is this nice city on nearby the sea in the north of Italy. And I work at the University of Genova. Specifically, I'm with the Department of Informatics, Bioengineering, Robotics, and System Engineering, also called DBRIS. And it is a medium-sized department, and as you can see from its name, it is a highly multidisciplinary department, of course with a strong focus on computer science and engineering. We have some bachelor and master degree in computer engineering, biomedical engineering, computer science, and also robotics and digital humanities. And you will see, I hope, from my talk that this multidisciplinary background is at the basis of my research. We also have two PhD programs. One is in computer science and system engineering, and the other one is in bioengineering and robotics, also in collaboration with the Italian Institute of Technology. Within DBRIS, I'm in the Perception and Interaction Lab. This is a sketch of the activities of my lab. As you can see, what we do is to design, to develop, and of course to study virtual and augmented reality system with a strong focus on the interaction part. So our main focus is to understand how humans interact within such kind of systems. This is a sketch of my research, of the research within my laboratory, the Perception Interaction Lab, and also an overview of the rationale behind my presentation, the presentation that I'm giving to you today. On the one side, we must study perception, human perception. In particular, what I did in the past and what I'm actually doing is to study visual perception, so to understand the mechanism of human perception, in particular of visual perception, and I try and I'm active in modeling such kind of mechanism. The knowledge about how visual perception works, how human perception works, helps in the development of the innovative human-computer interaction system, especially the one based on virtual mixed augmented reality. So our aim is to use the knowledge from what we know about humans in order to inspire the development of better interfaces. On the other side, we can use novel human-computer interfaces, novel devices, in order to help us in the understanding of the mechanism underlying human perception. So I'm in the middle of this loop, and you will see that this loop is what inspired my talk, the talk that I'm giving to you today. So I will talk about perception and interaction in virtual reality. During these days, yesterday, this morning, you have seen a lot of different devices. In this slides I have put some of the devices, but of course you can put in these slides all the amazing and interesting and exciting devices that have been presented during this conference and that maybe you are working with during your research, your activities, in your companies. So we have a lot of different devices. But there is something that is central, and it is in common with all the different devices that we can consider. And what is central, what is the common part, is the fact that there is a human being inside them. So such kind of devices are used by a human being, are used by a man or a woman that is wearing a headset, that is in front of the display, that is immersed in a virtual reality scenarios, or that is who is acting in an augmented reality system. And we have to take into consideration that there is a human being inside them, and that the human being is active, is acting inside such a kind of scenarios. And it is what I'm going to present to you. Let's start with an example. Okay, this is a video taken from the web, and it is a video like the ones that you have already seen that have been presented during this conference. It is a typical example of the use of immersive virtual reality, and it is virtual reality for maintenance. You have listened to a lot of different talk that explained how important and which are the advantages of using such kind of system, for example, for industrial maintenance. And it is true, we will see that there are a lot of advantages of using such kind of systems for training, for maintenance, to learn specific procedures. For example, you see that it is an example based on a headset, and the man that is in the bottom part of the video is interacting by using controllers. And you can see that maybe you can explore the various parts that compose an engine, for example. So you can see that it is the drive hand shield or the rotor, the bearing. So to interact within such system is very useful in order to understand the various parts that compose the system. And you can also learn how to disassemble a specific object. For example, you can learn how to disassemble this stuff or how to assemble it again. Okay, it is true, and of course we have a lot of advantages. But let's see in detail what the system is useful for. For example, this specific example that I have shown to you. First of all, it is very useful to familiarize with objects and instruments, so you can gain knowledge about objects that maybe you don't know, and maybe you have to explore in more detail. And of course, you can also handle this object, observe them by different point of view, so you can explore the fact that we are immersed in a 3D environment. And it is a positive fact. It is an advantage of such kind of system, of course. You can also learn a specific procedures. So such a kind of system are used with a great success in order to teach people how to perform a given task. In this example, how to assemble the engine. But there are also some actions, something that we cannot do yet. For example, it is impossible, it is very difficult, at least by considering this specific example, to learn how to handle objects and how to perform actions. If we focus on a frame, a specific frame of the video that I have shown to you before, you can see that, for example, the man that, remember, is acting by using controllers, like the Oculus Rift controller or the HTC Vive controllers, is handling this object that maybe is big and heavy by using an action that resembles a pinch action. And you know that in the real life, in real environment, is impossible to grasp an heavy object just by using the thumb and the finger with a pinch action. Maybe in the real world, we will handle this heavy object by taking it by using the two hands, or at least by using one open hand and using the anterior hand. So it is impossible to teach people how to manage, how to handle objects and how to perform actions. And again, if we focus on another frame of the video, it is impossible to, by using such specific example, to learn how to use a specific instrument. For example, if you look at the screwdriver, you don't handle the screwdriver, since your hands are occupied by the fact that they are handling the controllers. So you mimic the grasping of the screwdriver, but you cannot learn how much force to apply to the screwdriver in order to fix the screw in the correct manner in order to assemble your engine. So there are some open questions. One open question is how to solve the problems that are in the right column. Another example comes, for example, if you consider augmented reality, virtual or augmented reality. What we need is, for example, if you would like to highlight, like in the left example, give a specific part with, for example, the green arrow in order to give, to teach, turn that red tab highlighted by the green arrows. What we should have is what is called spatial colocalization. So we have to be very precise in order to put the instructions in the correct position. Otherwise, maybe the people would understand to turn the other red tab, the one that is on the right. Another problem is when we don't have a coherent alignment, so when the spatial colocalization is not properly achieved. So it is impossible to decide whether the bike, in the right example, is behind, below, beside the table, since there are errors in the relative depth in this example. Okay, these are open questions. We will discuss in a few minutes the implication of such kind of problem. But let's see other positive, well-diffused example of virtual reality. For example, this is an example of the use of virtual reality for a specific rehabilitation task. This is not an example of immersive virtual reality. It is a virtual reality achieved by using a large screen and a treadmill. And there are a lot of work, a lot of scientific work, a lot of research that demonstrate that there are a lot of positive aspects in the use of virtual reality scenarios, virtual reality system for specific rehabilitation tasks. For example, Parkinson is one of them. Another example is the use of virtual reality-based stroke rehabilitation. We can design, we can implement simple games, simple exercise game, in order to ask people to perform simple actions to recover from disabilities, from functionalities that have been lost from an injury, for example, from a stroke. This is one of the examples that you can find, and there is a lot of research, there are a lot of groups in the world, university, hospital, research groups that are working in this direction. Okay, what we can effectively do and what we cannot do yet by using such kind of devices. First of all, we can create different situations. We can exploit the fact that we can have a high level of realism. So not just exercises in an hospital room, so we can immerse people, and by doing this, rehabilitation, exercise become more interesting. We can also create ad hoc non-real situations. So we can exploit the fact that by using virtual reality, we can create situations that do not exist in the real life. It is the example of the virtual reality exposure therapy. So we can create an ad hoc scenario to rehabilitate from fears, for example, from the fear of spiders. So we can put spiders in this room, of course, in a controlled manner, in order to perform specific rehabilitation tasks. These produce a high level of engagement and motivation. This is of particular importance, for example, in specific situations. For example, the post-stroke rehabilitation. Often stroke happens to people that are young, still young, so not so old. And the engagement and the motivation aspect are very important. So people like to do exercise in virtual reality situation. And it is a good aspect. And we can exploit gamification. So we can exploit the fact that we can personalize the activities. So we can increase the difficulty of the game with respect to the improvements made by the people that we are, the user that we are rehabilitating. So again, all these are positive aspects of the use of virtual reality. And of course, there is the possibility of collecting and analyzing many kinds of data. So we can collect information about the movement of the patients, about the trajectories of his or her limbs, and we can also collect physiological data. And all these data can be analyzed by doctors, by researchers, in order to personalize again the rehabilitation training and so on. But we still have some open problems, and these are the problems that I would like to discuss with you today. One is, again, the fact that we are still missing a true ecological and natural interaction. We should discuss whether controllers are better than touchless vision-based interfaces. And I will show to you a specific example of this, since both solutions have the advantages and disadvantages. And the best compromise is still difficult to be achieved, to be found. Again, we have to take into account the fact that specific actions cannot be performed, like the example of the grasping that I have shown to you before. So we should replicate specific actions in order to be as natural as possible. And another open problem that is well known and highly discussed also in this conference is the fact that haptic and tactile feedback is still a problem. There are a lot of devices that are being developed, are being proposed also in this conference, and it is the proof that the problem exists, and it is a problem. Now I will show to you some examples that I did in my lab, and I will use this specific example in order to focus on a specific aspect of perception and interaction. Let's start from an example in augmented reality, an example that shows why a wrong perception is affecting interaction. Let's start from this example. This example is a user research. This user research, the task is very simple. Let me say trivial, but it is informative enough. We showed different virtual objects in front of people standing in a room. What we showed are virtual cubes, and virtual cubes appeared in a controller in a randomly controlled manner in front of the user. And the task was reach the cube. So touch the cube by using your index finger. So you see that the task is very, very simple. But by using this task, we can understand whether this simple action is performed correctly. The main question of this research are, first of all, if we are able to effectively judge the 3D location of virtual objects. So basically, if we put our finger in the exact position of the virtual object that we are displaying to people. Then we ask ourselves whether different types of augmented display have similar performances for the task. In particular, we analyzed the differences between the optical see-through and the video see-through technologies. And at the end, we ask ourselves whether the user is able to effectively interact with the augmented reality content. We considered an optical see-through device and a video see-through device, and we also considered two different situations. One is interaction by using the real hand. So we ask people to touch, let me say to touch, to reach the virtual object just by using the real hand. So people were able to see the real hand, and we asked them to use the real hand to touch the virtual object. And in another situation, we put a visual feedback. So we put a virtual representation of the hand. So people were able to see the virtual representation of their own hand. And we asked them to reach the virtual object by using the virtual hand. And why this? Since if we would like to design and implement a system intended to be used in training facilities, for example, in a manufacturing, we can ask ourselves whether interaction modality is better. So in which case interaction happens in a better way. These are the results. I'm not giving to you a lot of detail about all the results, but just an overview of them. You can see that if we in these plots, the red dot are the actual position of the virtual objects. So basically where we put the virtual objects, and the blue dot are where people put their fingers. What we can see that is that the first line, the top line, is referred to the video see-through technology, whereas the bottom line is the optical see-through. It is evident that video see-through, in this specific experiment, by using video see-through, people tended to put their finger closer to them, and there is an underestimation of the depth. So people perceive depth closer than the actual depth. There is also a difference between the first column and the second column. It means that the underestimation is more evident by using their own hand, whereas the underestimation is less evident if we use a virtual representation of the hand. We can discuss a lot about this result. The fact is that in the second situation, by using the virtual hand, we have a virtual alignment. So people tend to align two virtual things, the object and the hand, and everything is shrinked in a virtual environment and in the virtual reference system. Okay. This is another representation of the results, but we can skip it since it is more interesting to discuss a possible solution. You know, you have already seen, and maybe if you have tried some of the demos at the ground floor, that as soon as you are going to use an augmented reality device, a new device, you have to calibrate them. And maybe you have been told that if calibration is not performed, maybe the system is not working in a proper way. Yes, it is true. Devices are sold with their own calibration procedure. What we are actually doing is trying to explore whether a more complex calibration could be put in order to take into account the specific feature of the user that is behind the system. So besides using the calibration of in this case, the ATC Vive or the MetaVision that was the specific hardware that we used in this example, we developed a procedures that take into consideration all the possible translation, roto-translation among all different components of the system. I'm skipping again the results since it is interesting to see these two videos. Okay. In the first line, we have before calibration. The second line after calibration, I don't know whether it's a little bit slower, but doesn't mind. You see that before calibration, in some situation, one note, what we would like to have is the red checkboard correctly aligned with the black checkboard. And we can see that in the top line, there are some situations in which this alignment is okay. So by using the standard calibration, the alignment is okay. But if we stress the system a lot, that you see that in this case, the alignment is more or less correct. Okay, but if we put all the system very far from the device and we stress the situation, the alignment is no more correct. What we would like to obtain and what we were able to obtain, sorry for the video, but maybe it is too much to run two videos on the PC, you see that the correct alignment is always maintained. And it is what we would like to have, so a spatial colocalization of the virtual and the real elements. Okay, what we have learned from this first example. What we need to effectively interact in augmented reality system. First of all, a co-localization of real and virtual element. Okay, it is obvious. It is what most of researchers in augmented reality field and most of companies in the augmented reality field are trying to obtain. And year after year, new devices, new solutions in order to obtain this co-localization are released. And what we have demonstrated with this simple example is that if this co-localization is not perfect, and what I mean with perfect is that maybe the 1 centimeter of precision could not be enough. So we would need a very high precision in the co-localization. If this co-localization is not achieved, interaction becomes impossible, so it becomes prone to errors. To do this, we have to register the device reference frames. So all the devices, all the heterogeneous devices that play a role in your system should be accurately registered. And what we need is what we call perceptual calibration. So we need to take into account the man, we take to account the final user in order to take into account, just to give you an example, the fact that our interocular distance is different. So my interocular distance is different from yours, and also the distance from the left eye to the center of my head and from the center of my head to the right eye are different, so we are not symmetric, and all these play a role. Okay. Let's move to another example that I have anticipated before, and it is whether controllers, so the controllers, for example, the ATC Vive controllers or other controllers, are better with respect to touchless vision-based interfaces. Of course, we cannot decide during this talk whether it's better between controllers and touchless vision-based interfaces, but we can see an example. Again, the framework in which we performed the experiment. The experiment is very simple. We have this block. It is like the children game, and the task is grasp all the objects that are in front of you and put the objects in the correct hole in the grid that is, again, in front of you. Okay? We performed this task by using a lip motion and the ATC Vive controller. So we used two standard technologies. One, a standard vision-based solution, and a standard controller-based solution. Just an example of the experiment, and note that I have chosen this video since a young girl is performing the experiment, since the fact that different kind of people, so from young people to adult and even to elderly can use such kind of system, play a role in the discussion of the result. So you can see that the girl is grasping the object and putting them in the correct position, okay? It is, again, a typical situation like the ones that maybe you have already seen in many different applications. This is the same example performed by using the lip motion. Note that, and it is one of the things that will affect the result, you can note that she's lower, and it is demonstrated by the quantitative results that we collect. What we collect is the total and also the partial, I don't have the results, but also the partial time to complete the task. And what is obvious is that the completion time by using the ATC controllers averaged by considering all the participants to the experiment is considerably slower with respect to the completion time by using the lip motion. Also the standard deviation, so the distribution of the timing is higher by considering the lip motion with respect to the controllers. So we can say that to solve this specific task with controllers is better with respect to the lip motion. But we have to consider different aspects, and I'm proposing to you something to think about. One is the fact that, of course, in this case, the ATC5 controllers are based on robust tracking algorithms. You know that the tracking algorithms of such kind of device is robust. They are not affected by occlusion. If you remember the videos that I have shown to you, you can say that you can remember that the girl that was interacting was putting the controller also behind her, and the controller still work. It is not possible by using a vision-based controller that has its own field of view. And again, controllers are not dependent on a hand model. If you remember, I stressed the attention that, and I intentionally put the video collected by using a girl, since if you use the lip motion, you have an hand model, and in many situations this hand model is not working properly. Maybe, for example, when you consider children. Children have a very specific shape of their hand, so the thumb is not is different from the thumb of an adult hand. On the contrary, vision-based controller rely on computer vision algorithms. And computer vision algorithms are very robust nowadays. There has been a lot of improvement in the computer vision fields, yes, of course, but they are prone to errors due to illumination changes, due to noise. There are a lot of environmental noise that are going to affect the measure taken from a computer vision algorithm. They are affected by occlusion. If I put a hand outside the field of view of the controller, it is not possible to detect the position of the hand and to detect the 3D position of the finger. And they are dependent on a hand model, like I have discussed before. But there is an important thing that we have to consider. They allow bare hands interaction. If I'm handling a controller, my hands are occupied by the controller, and I cannot handle any other kind of instrument. So if I would like to interact by using an instrument and I have a controller, I cannot handle at the same time the controller and a specific instrument. Remember the example of the screwdriver that I have shown in the previous example. And it is something that it is important to achieve a natural interaction, since I interact in the environment by using my hands. Now I'm handling this controller, since I need this controller, but it is my own decision. My hands are free, okay? And I live in an environment where my hands are free. Another important aspect is that haptic feedback is missing. I have mentioned the fact that there are a lot of attempts to replicate the haptic and the tactile feedback inside virtual reality, since you know that the haptic feedback, the tactile feedback is missing. If you think about the gloves, for example, there are some examples of very interesting gloves at the ground floor in this conference. What gloves are doing is to try to cheat our system and putting some vibration, and vibration are trying to replicate the tactile feedback. Of course, we are not touching anything, but the vibration are, in a certain sense, giving us the impression of touching something, okay? There are also a lot of research, and it is something that we did, to try to cheat our system by using other feedback. In this case, we consider a visual feedback. For example, if you see the hand, you see that there is an orange object like this. When we reach the object becomes blue. When we release, we touch the object, but we release it, the object is gray. Okay. What we did is to understand whether this kind of additional feedback, in order to try to replicate the missing haptic feedback, play a role or not. And unfortunately, what we obtain is that more or less the time remains the same. So it is difficult to cheat our system. So it is difficult to give to our perceptual system the impression of touching something by using, for example, an audio feedback or a visual feedback. Maybe if we had a fifth column, by using a vibration, for example, by using something like a glove, we would obtain a slower timing. But it is not the focus of this slide. The focus is that the tactile feedback is missing, and it is difficult to replicate it inside virtual environment. And it could be a problem. It could be something that we have to think about. So to conclude this example, to find the best compromise we have to find the best compromise between robustness and naturalness. So on the one hand, we would like to have a robust interaction. On the other hand, we would like to have bare hands interaction. And of course, we would like to have the haptic feedback. So these three elements are what we would like to have, would like to obtain in an ideal interaction system in virtual reality. And it is what we would like to have, and what hopefully technologies will give to us in now, in the future month, and so on. Another question is that I would like to propose to you is whether we grasp objects in virtual reality like in the real world. What does it mean? It is this specific example is an example that we did in collaboration with a group of psychologists in Germany. And what we would like to understand is if existing interaction techniques, so the interaction techniques that we learn when we were a child, when a child is born, he start learning how to interact with objects, and now we are able to interact with objects. So if I would like to grasp this bottle, I perfectly know how to grasp it. What we ask ourselves is whether, for example, to grasp a virtual battle, not a real battle, but a virtual battle, is performed in a similar way, or if we are acting by using different strategies. Why it is important? Since it is important to understand whether our brain is asked to learn something different, to learn different strategies to interact with objects. Let's say an example. This is an example in the real world, so it is not virtual world, but it is an example performed by a group of psychologists in Gießen. So what they did is to observe and to collect data by looking at simple grasping actions by considering unfamiliar objects, so not objects from our real life, but unfamiliar 3D objects. You can see that as soon as we would like to grasp this object, we put the finger in a given position, then we close the finger, and we are able to lift the object up. Of course, we can decide to perform an unstable grasping, so we can grasp on the other side and the grasping will be unstable. We can decide to do an uncomfortable grasping by putting the finger in an uncomfortable situation. But of course, we cannot grasp the object by using this finger configuration. Okay. And if we plot the data that have been collected, we see that we can find specific pattern, and people tend to put the thumb that is in red and the index finger that is in blue in specific situation. What we did is to replicate this example in virtual reality. So this is our virtual reality setup, and it is exactly the same. So randomly, the same object that you see before appear, and we ask people to grasp the object and to put it on his right side. You see that, in this case, people are going to grasp the object in the correct way, so they are putting the finger like in the real world. If we continue to watch these, for example, okay, you see one of the main problems of such kind of interface. You see that, in this case, people tend to put the finger inside the object. This is one of the typical drawback of virtual reality. So it is something that is a little bit different. but again, interaction happens in a similar way. And if you continue, there are, sorry for the timing, but it is to replicate the exact timing of the real world experiment. And, okay. You see that if we put this is an uncomfortable grasp. And again, the action is similar. We have to try several times before being able to grasp the object. And we can continue to watch the video, but what we did is to collect all the data and to try to replicate the data collected in the real world. And more or less the situation is the same. So people tend to put the finger more or less with a similar pattern with respect to the real environment. It is a very interesting result, since people do not do any uncomfortable or impossible grasp. They tended to put their finger in more or less near the body center of the object. So the behavior is absolutely similar to the one of the real situation. So we observed similar patterns, both between subject and within subject. Of course, by using virtual reality, we can play a lot with this experiment. So we can put texture and we can play with the physics of the virtual reality object. So we can use, and if you remember my first slide, we can use virtual reality to know more about our perceptual system. So we can devise different experiments inspired by our intuitions. So we can play with texture, with physics. We can put the body center of the object in a different position, and we can continue such kind of experiment in order to understand a lot about our perception and about the strategies, in this case, to grasp. And of course, we can also try to understand how grasp happens in mixed reality. So maybe we can put a headset on and to show something, but ask people to grasp a corresponding object. So we can put a texture of a heavy object, but asking him to grasp a light object or vice versa. And again, it is very interesting, and it is something that research would continue to do. Okay. The last example, I would like to finish my talk by talking about mixed reality. So I start with augmented, virtual, and now an example in mixed reality. So I would like to understand, to show to you an example of interaction in when there is the combination of a physical and a virtual environment. The specific application is medical training and simulation, since it is in collaboration with the Simulation Center of the University of Genova and one of the main hospitals in Genova. And what we did is to devise simulation scenarios. You know, I don't know whether you are expert of medical training, but medical training is necessary in medicine, since simulation is training, and it is essential when the knowledge of specific procedures is mandatory. And this translates in a reduction of errors, since if we train people, if we train doctors, they will do less errors, of course. Typically, in hospitals, simulation is performed by using physical mannequins. Physical mannequins are like dolls, okay? And there are a lot of sensors integrated in such kind of dolls. And there are a lot of advantages, since these sensors are able to replace the anatomy and the real physiology in answers to actions performed by students and doctors. So we have mannequins to teach how to deliver a baby, for example, or how to perform specific surgical operation. But there are a lot of disadvantages. One is that they need to have a dedicated place, and this dedicated place is not like in the real life. It is like an aseptic room, in the simulation center. And they have a low level of truthfulness. And doctors are aware of the fact that it is a problem, since they learn to act by using a doll whose appearance is like a doll. And it is very difficult to apply the same procedures when, at a certain point, you will have in front of you a real human being, for example, a child, or a human being that is suffering from pains and so on. So, on the other side, nowadays, there are a lot of attempts of using virtual reality. The main advantages of virtual reality is that we can insert the trainee directly inside the simulation. So we can simulate different scenarios with a high level of realism. But again, we have to take into account that there are disadvantages. One is the fact that the tactile feedback is missing in virtual reality. And when we are considering surgical training, medical doctor training, the tactile feedback is one of the most important aspects. And again, the problem is the fact that in many systems we don't have an ecological interaction. It is why a mixed situation, so a mixed reality system could help us in solving the problem. You can see the prototype of our mixed reality scenarios. You can see on the right side that the guy is directly interacting with the mannequin. So he can use all the sensor. Okay, he can use all the sensors that are in the mannequin. So he can exploit the good aspect of physical simulation. But on the other side, you can see that he's wearing an headset, and you can put this mannequin, you can put a real appearance on the mannequin, and you can contextualize the scene by putting the mannequin, for example, in this street to simulate a car accident and so on. And a small focus on interaction. The interaction in this case is a bare hand interaction. Of course, we are aware of the fact that emotion has its own limits, but we are also aware of the fact that to do simulation, people should also use instruments typical of the medical training. So the hands should be free. And it is why we are using bare hand interaction. So the guy is interacting with his real hand, but he is seeing a virtual replica inside the virtual reality. Okay, to do this, it seems everything has been done, but we must evaluate how well the virtual model is mapped onto the real mannequin, since one of the biggest problem is that if it is absolutely necessary, then that as soon as we touch the real mannequin, exactly the same action is replicated in the virtual element. So the alignment between the virtual mannequin and the real one should be perfect. At the moment, it is not so perfect, but a user evaluation, so we performed a user evaluation training, and we obtain a good result for the 75% of the points, and the system has been appreciated in terms of immersivity and presence, both from expert and non-expert, and it is a good point. Okay, so what we have to think about is the precision of the alignment, of course, the presence of the haptic feedback, the possibility of adding real and virtual instruments. So in this situation, we can use real instruments and we can put their virtual replica inside the scenarios. But of course, we should co-localize again also the instruments. So a precise tracking, 3D tracking of the instrument is also necessary, and it is not trivial. But of course, we can also think about other interaction devices like gloves. These are the key aspects that we have to consider to have an effective working system. But the advantages of mixed reality, I think that are evident. Okay, this concludes my talk. This is my group and my collaboration, and of course I'm happy to answer to your question if any, and thank you very much.